Hi, my name is Bruce, and today I'm talking about some joint work with Serhat Arslan and Nick McEwen on sizing buffers in internet routers. This is an example of internet routers. Packets come in onto these cables, the router figures out where the packets want to go, and then it sends it out another cable. Inside this router, there are buffers. When a packet comes in from a cable, instead of being sent out immediately, it's put in some buffer, and then later on, when the cable is ready to send some new packets, a packet is removed from the buffer and it's sent out into the internet. The reason for these buffers is if we have a whole bunch of packets which all arrive at once along these different cables, we can put them into the buffer and then we can send them out when we have some time to, instead of having to throw away some of these packets. There's been this long-standing question about how big a buffer needs to be in an internet router, and there's sort of two ways of thinking about answering this. The first one is for applications or people who use buffers. For applications, buffers can either be too big or too small. If the buffer is too big, then we have these big queues where packets are waiting around waiting to be sent, which increases delay, which increases buffer bloat, and tends to make things worse for applications. If the buffer is too small, then we can't handle bursts of packets, and we throw away more packets than we need to. For router manufacturers who have to build these routers and put the buffers in them, there's also some trade-offs with buffer sizing. If they build the buffer too big, then they have to do some more work to engineer this router. Like in some cases, if you have a small buffer, you can fit this buffer on the same chip that does the routing. But if the buffer gets big, you have to put it off the chip, and then you need to spend a bunch of bandwidth going back and forth between these two switches that you could otherwise use to send packets around the internet. But if the buffer is too small, if you get this size wrong, then people might not actually buy the router because it might not work well for their applications. So the question is how big the buffer should be. There have been a few answers to this question of how big a buffer needs to be. In the 90s, Jacobson and Villemiser and Song argued that you need a buffer at least as big as a BDP, or the bandwidth delay product, in order for one TCP Reno flow to fully utilize a link. Here the BDP, this is the product between the bandwidth of the link, like 10 gigabits per second, and the end-to-end delay for a packet to be sent from the sender to the receiver and back across the link. For TCP, this is the number of packets we need in order to even hope to fully utilize the link. And so what this means is that we've got some bandwidth delay product worth of packets in the network. We have some BDP worth of packets sitting in the buffer. This is like 100% overhead. And this 100% overhead is necessary in order to get full link utilization. There was another rule of thumb from 2004 by Appenzeller, McEwen, and Kessley, which is known as the square root of n rule. And this rule says that you need a bandwidth delay product over the square root of the number of flows which are all using the link. So as more and more flows start to use a link, you're able to get away with a smaller and smaller buffer. Since 2004, a lot has changed in the internet. In 2006, Cubic replaced Reno as the default Linux algorithm. In 2011, Linux introduced an algorithm called PRR, which changes the way that Reno responds to a loss and breaks the argument for the usual BDP rule. And in 2016, Google introduced BBR, which even further changed the way we do congestion control. So those two rules of thumb are for TCP Reno flows. And a lot has changed in the way we do congestion control. Like for instance, we no longer use Reno in the intervening years. And so the question is, how big does a buffer need to be today? In our paper, we focus on how different choices made by TCP impact buffer size requirements. In doing so, we come up with new rules of thumb which give the buffer size required for full link utilization for modern implementations of TCP, which include algorithms like PRR, Cubic, and BBR. We also look at the relationship between buffer size and link utilization. Buffer size rules of thumb are typically to get 100% link utilization, and we show that if we relax this just a little bit, we can still get very high link utilization with a much smaller buffer size, for instance 99% link utilization. In general, our paper shows that buffers can be made smaller by making better choices at the TCP layer. Here's an example of some of our results for a single TCP flow. We look at a number of different algorithms, including Reno, Cubic, BBR, and scalable TCP, and we look at buffer size required for full link utilization and partial link utilization. We recover the usual BDP rule for Reno under full link utilization, despite the many changes to TCP that have occurred in the past 2 or 3 decades. We also show that for pretty much any other algorithm, or anything less than full link utilization, you can get away with a much smaller buffer. For instance, if you're interested in using BBR, in order to get full link utilization, you only need a buffer which is a quarter of the usual buffer size required for Reno. If you're happy with 90% link utilization, you can get away with a 15% buffer. So these are our results for a single flow, and you can look at more about the details of them in the paper. What I'd like to spend the rest of the talk talking about is our results for multiple flows. And as a reminder, let me restate the state of the art here. So this is the rule of thumb for multiple TCP Reno flows, which comes from a paper of Appenzeller, McEwen, and Kessler in 2004. And this result is known as the square root of n rule. This result says that if the buffer is at least as big as the BDP over the square root of n, where here n is the number of TCP flows which share a link. And then, so if the buffer is this big and then some conditions apply, and I'll talk about these conditions in a second, then the link will be fully utilized. And what this says is that if we have some buffer requirement for a single TCP Reno flow, as more and more flows start to use the link, you can get away with a smaller and a smaller buffer. But there are some conditions for this result, and these are the conditions. The conditions are that TCP sends data at a rate which is a random variable, and this random variable is uniformly distributed around BDP over n. And not only are these random variables, but among all the flows which are using the link, the random variables are independent and identically distributed. So these are really difficult conditions to believe. We don't actually believe that TCP Reno sends data at a rate which is a uniform random variable because we can measure it and it doesn't. We also don't believe that TCP Reno is independent because if I tell you the window sizes, the amount of data that all of these TCP flows are sending, and then I ask you what the rate is for the last one, like you actually have a lot of information, a good guess about what this last one is because of fairness. So these are the conditions. The conditions are hard to believe, and yet somehow when we run experiments, the square root of n rule still holds. And so our question was like, what is it about TCP, especially TCP Reno, that like allows this sort of rule to hold? And so we looked into this, and we were able to prove the following result. If n flows share a link, and we have some conditions, and I'll talk about these conditions again in a second, then provided the buffer is at least as big as the bandwidth delay product over the square root of n, the link will be fully utilized. So we recover the usual square root of n rule. But we also go a little further and say that no matter what buffer size you have, the utilization will always be at least 1 minus something like 1 over the square root of n. So both buffer can get smaller as more flows use the link, and also utilization gets higher as more flows use the link. And for our conditions, we have two conditions. The first condition is that flows are fair, in the sense that they all send roughly the same amount of data into the link. And this, we believe, is a fine condition, because this is the sort of thing that TCP wants to enforce. The second condition is that flows are desynchronized, and that only a few flows will decrease their windows, will like slow down the rate that they're sending at any one time. And we'll come back to these conditions in a bit. But for now, let me just state what the theorem says. So let's say we have a link, and this link is shared by 10,000 Reno flows. And this might be a sort of natural setting when you have a big internet link with a lot of traffic going across it. So our result says that you can get full link utilization provided the buffer is 100 times smaller than the buffer required for one TCP Reno flow. Our result also says that kind of no matter what buffer size you pick, your utilization will always be at least 99%. So if you have a link with 10,000 Reno flows and you're happy with 99% utilization, it kind of doesn't matter what buffer size you pick because you will always get utilization that high. Now I'd like to talk about these two conditions for the theorem. And in order to do that, let me build up a little bit of intuition about why we could expect a result like this to hold. And the intuition is as follows. Suppose we have something like the following. On the x-axis is time, on the y-axis is queue depth, and it shows the queue depth over time for some process which is using the queue. This dotted line at the top here is the buffer size. And the queue, there's a sort of a big queue that's hanging out, something we might call a standing queue. So the queue starts out high, and it gets higher until the buffer fills up, and then it backs off a bit. But it doesn't back off that much. The queue still remains full. And so if we think about this, if we think about how big the buffer ought to be in this setting, it feels really natural to think that we should be able to make the buffer smaller, right? We should be able to just crank the buffer down, get rid of this standing queue, and get away with the smaller buffer. But this is a pretty big assumption, right? Because TCP is some algorithm, and the algorithm depends on the buffer size, and so it can do anything it wants, like in response to the buffer size. It might have nice behavior like this, but it might also just go totally wild and do something bizarre. What we show in our paper is that this intuition is actually true. If TCP is varying some amount and has some standing queue, you can actually reduce the size of the buffer, get rid of this standing queue, and TCP will behave the same in terms of link utilization. So with that intuition in mind, now we can talk about these two conditions. So the first condition is about fairness, or the amount of data that each TCP connection has in the network at once. And the reason fairness matters is because when TCP slows down the rate it's sending, and therefore causes a decrease in the queue depth, the amount that it slows down is proportional to the amount of data it has in the network. And this is true for Reno, it's true for Cubic, it's true for BBR, and it's true for other congestion control algorithms. So here's an example of this from some experiments we ran in the paper. On the x-axis is time, on the y-axis is queue depth, and it's the queue depth for 4 TCP Reno flows which are all sharing a link. As time goes on, we see a drop in queue depth, and this drop in queue depth is caused by 2 flows both seeing a loss at the same time and dropping their windows. But then as time goes on even further, we see another drop, about the same decrease in queue depth, and this time it's caused by 1 flow, which has a really big window, which is decreasing its window. And then finally we see a drop which is about twice as much, and this one is caused by all the flows simultaneously decreasing their windows. And so what I'd like to point out here is if we have one flow with a really big window, this will cause a higher increase in queuing variability, and this will cause a higher required buffer size. The other condition we have is about synchronization, which relates to how often the flows back off at the same time. And the reason this matters is because if all of the flows back off at once, like we just saw in the previous slide, we see a much larger change in the queue depth. So here's an example of this from an experiment we ran in the paper, and you can look at the paper if you want to know the details of what we ran an experiment with. But we basically tested 2 things. One thing caused a lot of synchronization, and the other thing didn't cause any synchronization. This blue line is the behavior with synchronization, and we see a very large change in queue depth, which by our intuition relates to a larger required buffer size. These are conditions for the theorem, and we wanted to argue that these conditions hold in practice, so we ran some measurements in a testbed. This is a graph of how the queue depth responds when there's multiple different numbers of TCP flows all sharing the same length. Each row here is a different number of flows, ranging from 1 flow at the top to 128 flows at the bottom. Each row is the distribution of queue depth when we have a bunch of flows all using the same length. You can see with 1 flow, the distribution is pretty spread out, and we see a pretty even amount of queue depth. But when we start to increase the number of flows, the distribution shifts to the right, and we build up this large standing queue. This large standing queue, by our intuition, suggests that we can make the buffer smaller, and we show more experiments in the paper. So these results hold in practice, but especially this condition about synchronization, this is still an assumption. And if you're designing a new congestion control algorithm, if you're running a different network, you might want to avoid having to make this assumption about synchronization. In the paper, we talk about different ways to do this, and one of the main ways is you can add a little bit of randomness that sort of enforces a lack of synchronization among the different flows. In our paper, we show that you can actually prove square root of n results without any assumptions about synchronization for both BBR, which uses randomness, and a variant of Reno, which adds a little bit of randomness to the way it decreases our window. To conclude, we should only really need small buffers in networks. Our results show that modern TCP algorithms require much smaller buffers than TCP Reno, buffers which are fractions of the size of TCP Reno. Our paper also talks about the relationship between buffers and utilization and shows that this is a consequence of the different choices we make when we're doing congestion control. We show that by making better choices with congestion control, we should make the buffers smaller. And as kind of a long-term goal, we believe that we should be able to get away with buffers of between 10 and 100 packets by making better choices with congestion control algorithms. There's a lot more about buffer sizing that we still need to understand. In our paper, we focus primarily on link utilization, but even for TCP Reno, we don't understand how other things we care about, like loss and fairness, are impacted by buffer size. We also don't understand how things we care even more about, like whether or not an application works well. We don't understand how these things are impacted by buffer size either. Finally, if you are running a network today, we actually don't know what buffer size will give you the best performance in your network. We would encourage you, if you are running a network, to run some experiments and see what kind of buffer size works well for you. If you're working on applications, we would encourage you to think about the sort of buffer size requirements that are imposed by your applications. We believe that by doing this sort of work, by investing this sort of time, we should be able to dramatically reduce the size of buffers in the network, and improve the performance for applications and for people who build routers. Thank you.